Hello there, and welcome to Earth Files, where quiet curiosity meets the slow rhythm of the planet, and wonder is allowed to take its time. Tonight, we are not rushing toward the edge of space or peering at the far reaches of the universe. Instead, we are looking right at home, beneath our feet, around our atmosphere, across our oceans, and above our skies. We are here to notice the remarkable balance of conditions that make life possible, and to reflect on how Earth, in all its complexity, supports us in ways so delicate and precise, it can feel almost intentional. Before we dive in, I would love to know where you are listening from tonight, and what time it is where you are. It is a small act of connection, a reminder that we are sharing a moment across distances and time zones, quietly joined in attention and thought. If this kind of slow, reflective exploration of our planet appeals to you, I would be thankful if you tapped like or subscribed. It helps this gentle signal reach other curious minds, extending our shared observation of Earth's wonders. Now, settle in, perhaps lie back, close your eyes if you like, and allow your thoughts to drift slowly, as if floating above the planet itself, seeing it from a distance, yet intimately connected to every detail. Earth is extraordinary, even if we often take it for granted. Its surface, its atmosphere, its oceans, its crust, its magnetic field, its distance from the sun, all of these factors combine in a delicate balance that sustains life. And when we begin to trace the reasons life thrives here, we notice one consistent truth. Each of these conditions is neither trivial or random in its impact. The simplest of shifts could have made Earth unrecognizable, inhospitable, or entirely lifeless. Let us begin with the first and most obvious factor: Earth's location in the solar system. The sun is our source of energy, of light and warmth, yet it is not too close, nor too distant. This placement is often called the Goldilocks zone, a range of distances where water can remain liquid on a planet's surface, to near, and the heat would boil oceans away. Too far, and water would freeze into permanent ice, and any life that requires it would struggle to exist. Earth sits in that delicate band, warmed gently, consistently, by the sun's rays. Day after day, year after year, the energy flows steadily, neither extinguishing life with extremes, nor denying it the warmth to grow. The tilt of Earth's axis is another quietly stabilizing factor. At approximately 23.5 degrees, it gives us seasons, but they are moderate, never extreme enough to make the surface uninhabitable. Summer and winter dance across latitudes, rivers rise and fall, forests change color, and life adapts to the rhythm. With a tilt significantly different, the climates could swing violently, glaciers might dominate permanently, and deserts might expand uncontrollably. The stability of this tilt is largely owed to the presence of our moon, a celestial companion that quietly governs the wobble of Earth's rotation, ensuring that over millions of years, seasons remain predictable and life has the time and space to evolve steadily. Water itself, the medium of life, is another wonder of Earth. It exists abundantly on the surface, flowing in oceans, lakes, rivers, and clouds. Its chemical structure is unique. It expands when frozen, contracts when warmed, dissolves countless minerals, and transports nutrients across landscapes. Water moderates temperature, distributing heat across the planet, softening extremes between day and night, and between equator and poles. It participates in a cycle that is continuous and unending: evaporation, condensation, precipitation, and runoff, carving valleys, shaping mountains, and sustaining the smallest microbial life. In every drop, we find the fingerprints of chemical precision and the conditions that make life possible. Without water in this balance, Earth would be a dry, barren rock, incapable of sustaining the diversity we see today. The atmosphere adds yet another layer of subtle protection. It is thin enough to allow sunlight to reach the surface, yet thick enough to shield us from harmful radiation. Its composition is rich in nitrogen, stable and inert, forming nearly 78% of the air we breathe. Oxygen, essential to complex life, makes up around 21%. Trace gases, including carbon dioxide and argon, play quiet roles in moderating climate and facilitating biological processes. Without this balance, the planet could quickly overheat or freeze. Storms might become uncontainable. Radiation from the sun would strike with lethal intensity. The air itself, often unnoticed, is a finely tuned medium for sustaining life. Earth's magnetic field is another invisible guardian. Generated by the movement of molten iron within its core, it extends far into space, forming a protective bubble against cosmic radiation and charged particles from the sun. Without this field, our atmosphere would be stripped away over time, much as we see on Mars. The magnetic shield is silent, unseen, yet its effects are critical, preserving the air we breathe, the oceans we swim in, and the soils that feed plants. It allows life to flourish on the surface instead of retreating underground or being destroyed by energetic storms from the sun. And beneath all of this, Earth's crust is constantly renewing itself. Plate tectonics drives the movement of continents, the rise of mountains, and the recycling of carbon. Volcanoes release gases into the atmosphere, contributing to the balance of heat and chemistry. Earth is not static, it is dynamic. The continents drift slowly over millions of years. Oceans open and close, and life adapts alongside these monumental shifts. Without this slow geological rhythm, the carbon cycle would falter, the atmosphere might become inhospitable, and the evolutionary opportunities we now take for granted would be impossible. Even the extremes of Earth's environment tell a story of balance. Polar ice caps store water, regulating sea levels and reflecting sunlight. Deserts absorb heat, driving atmospheric circulation and rainfall in other regions. Storms and currents redistribute energy across the planet, maintaining a dynamic equilibrium. Every extreme has a compensating factor, creating the intricate system in which life not only survives but thrives. One could pause and consider the long arc of time. Earth formed approximately 4.5 billion years ago. Life emerged around 3.8 billion years ago. Oxygen appeared in the atmosphere other than 2.4 billion years ago, and multicellular life became possible only after hundreds of millions of years of adaptation. Each stage relied on the conditions that came before. Without stable water, without atmosphere, without plate tectonics, without a magnetic field, life could not have reached the complexity it did. And yet, life adapted to slight fluctuations, using constraints as opportunities. The planet itself and the life upon it became partners in a slow, interdependent dance. As we reflect on these facts, it is easy to be struck by the subtle improbability of it all. Not improbability in the sense of magic, but in the quiet, cumulative wonder of natural processes aligning. Earth is not perfectly predictable. Its climate fluctuates, ice ages come and go. Volcanoes erupt, asteroids strike. Yet somehow, despite shocks and upheavals, the planet remains within a range that allows life to persist. It is a balance of forces, some chemical, some physical, some gravitational, that coalesces into the remarkable conditions we experience today. From this perspective, one might say that Earth appears designed, not in the sense of deliberate creation, but as a result of remarkable fine-tuning. The distance from the Sun, the presence of water, the thickness of the atmosphere, the stabilizing influence of the Moon, the magnetic field, and the ongoing processes of plate tectonics all combine to create a hospitable environment. Life is a beneficiary of these conditions, adapting and evolving in response, shaping and being shaped by the planet over billions of years. Even now, when we step outside and breathe, when we see the ocean or a forest, we are participating in that system. Every tree, every organism, every drop of rain is part of a network of balances that have persisted through catastrophe and survival. The air we breathe carries oxygen that was first released by ancient microbes. The soil beneath our feet contains minerals recycled over eons through tectonic processes. Every aspect of the living planet is intertwined with its physical and chemical systems in ways that are both extraordinary and deeply subtle. And yet, despite this intricate balance, there is still room for imagination and reflection. We do not need to speculate wildly to appreciate Earth's uniqueness. Simply noticing the combination of factors, the careful alignment of planetary conditions, is enough to inspire awe. It reminds us of the fragility of life and the remarkable persistence of a planet that has supported it for billions of years. It invites gratitude, not only for our immediate surroundings, but for the entire chain of events that led to our existence. So, as we begin this journey together, let us carry both attention and calm. Let us observe Earth in its quiet complexity, appreciating the balance that allows life to flourish without needing to rush toward conclusions or answers. Let us notice how oceans, skies, rocks, and air work together in patterns that are both intricate and resilient. Each system influences the others in quiet, ongoing ways. Winds sweep across oceans, driving currents that carry heat and nutrients from one part of the world to another. Mountains and valleys guide airflow, creating regions of rainfall and aridity. Rivers carve their paths, moving sediments to oceans, where they are slowly deposited and recycled. Life itself interacts with these systems. Phytoplankton floating near the ocean surface produce oxygen, feeding both water and atmosphere. Trees along riverbanks stabilize soils, drawing water from the earth and releasing it into the air. These interactions are subtle but constant, forming a dynamic balance that sustains life over vast spans of time. Consider the oceans more closely. Covering over 70% of Earth's surface, they are vast reservoirs of energy, heat, and nutrients. Ocean currents act as the planet's circulatory system, moving warm water from the equator toward the poles and returning cooler water toward the tropics. This redistribution moderates climate, keeping equatorial regions from overheating and polar regions from freezing completely. The mixing of water at different temperatures also brings oxygen into deep layers, supporting life in regions far from sunlight. In every drop, the ocean carries the story of the planet's energy, chemistry, and biological processes, quietly sustaining life across scales, both immense and microscopic. Beneath the surface, life persists in forms that challenge imagination. Hydrothermal vents, deep in the ocean, where sunlight never reaches, release mineral-rich fluids heated by Earth's molten interior. Microbial communities thrive in these extreme environments, deriving energy from chemical reactions rather than sunlight. These isolated ecosystems are relics of early Earth, places where life may have first experimented with metabolic processes. They demonstrate how resilience and adaptability are fundamental to life, even when conditions appear harsh or inhospitable. Life finds a way, wherever energy and nutrients allow it, slowly shaping its environment, even in the most extreme conditions. Water's role extends beyond its chemical and physical properties. Its cycles influence climate over centuries and millennia. Evaporation from oceans forms clouds, which move across continents, releasing rain that nourishes forests and replenishes rivers. Snowfall accumulates on mountains, storing water that melts gradually in spring, feeding streams and maintaining ecosystems downstream. Even in deserts, rare rains trigger rapid bursts of plant growth and microbial activity. Water connects distant regions, linking ecosystems through its circulation. It is the lifeblood of the planet, enabling life to flourish while simultaneously shaping the very landscape that life inhabits. The atmosphere itself is a system of astonishing balance. Composed predominantly of nitrogen, with oxygen, carbon dioxide, and trace gases, it provides both protection and opportunity. Nitrogen acts as a stable backdrop, preventing rapid chemical reactions that could threaten life. Oxygen, a product of photosynthesis, enables complex life and forms a delicate balance with carbon dioxide, regulating climate. Trace gases such as methane and ozone play roles in heat retention, chemical reactions, and ultraviolet shielding. Variations in these concentrations over geological time have triggered ice ages, mass extinctions, and evolutionary bursts, but the overall balance has remained within limits that allow life to persist. The interplay between oceans and atmosphere is particularly remarkable. Heat stored in ocean waters influences weather patterns, distributing warmth and driving storms that carry energy and water across continents. Large-scale phenomena like El Niño and the monsoon systems demonstrate the dynamic interaction between water, air, and the rotation of the planet. These patterns have profound effects on life, influencing migrations, reproduction cycles, and ecological niches. Even subtle changes in these interactions can ripple across ecosystems, illustrating the delicate complexity that underlies Earth's habitability. Earth's crust, mountains, and tectonic activity contribute further to this balance. Continents rise slowly over millions of years, shaping climate by redirecting winds and currents. Mountain ranges act as barriers to atmospheric circulation, creating rain shadows and fertile valleys. Volcanic activity releases gases that replenish the atmosphere and contribute to greenhouse regulation, while also supplying minerals that nourish life. Plate tectonics slowly recycles carbon and other elements, preventing long-term accumulation that could destabilize the climate. Life and geology are intertwined in a slow, patient dance, each influencing the other across eons. Even extreme conditions, such as glaciations or droughts, play roles in the broader narrative. Ice ages reflect feedback loops between sunlight, greenhouse gases, and ocean circulation, cooling the planet and reshaping ecosystems. Species must adapt or retreat, and new evolutionary opportunities emerge in response to these stresses. Similarly, droughts and fires, while destructive locally, can trigger succession in ecosystems, opening niches for new life forms. The planet's capacity to withstand and recover from extremes is part of its resilience, and water, air, and land are central to this restorative ability. The chemical cycles on Earth reveal another layer of remarkable balance. Carbon cycles between atmosphere, oceans, and land, moderated by photosynthesis, respiration, and decay. Nitrogen cycles through soil, water, and atmosphere, driven by microbes that convert it into usable forms for plants. Oxygen, essential for complex life, is produced and consumed in a delicate equilibrium maintained over billions of years. Even trace minerals and elements circulating ways that sustain organisms across diverse environments. These cycles illustrate that life and planet are codependent. The planet provides the chemistry necessary for life, and life maintains the chemistry necessary for stability. Observing life in these systems, one sees the ingenuity of adaptation. Microbes colonize surfaces, thrive in extremes, and shape their environment, altering chemical conditions and preparing the way for new life. Plants harness sunlight, transforming carbon dioxide into energy, while creating oxygen as a byproduct. Animals exploit niches created by others, forming complex food webs that maintain ecological balance. Every organism is both a product of its environment and a participant in the ongoing shaping of that environment, a contributor to a system far larger than itself. Water and atmosphere also preserve memory. Sediments record the history of oceans and rivers, while ice layers archive ancient atmospheres. Rocks contain isotopic signatures that reveal climate cycles and major events such as glaciations or volcanic eruptions. Life itself leaves traces. Stromatolites, fossils, and chemical byproducts indicate the presence of photosynthetic microbes billions of years ago. In every layer, every sample, every molecule, we find evidence of the intimate connections between water, air, rocks, and life. The planet writes its own diary, subtle and patient, waiting for observers to notice. Even small processes matter. Rain falling on soil carries minerals into rivers. Tide pools experience fluctuations that challenge life to adapt. Clouds form and dissipate, shading landscapes and affecting photosynthesis. Over time, these minor interactions accumulate into large-scale patterns, shaping climate, geology, and evolution. Life, while resilient, is attuned to these cycles, responding over generations and eons. The subtlety of these processes illustrates that Earth's systems are not simply chaotic, they are integrated, dynamic, and surprisingly stable over long periods. Consider the resilience of oceans during planetary extremes. When ice ages encase continents in glaciers, life persists in deep seas and isolated pockets of liquid water. Microbial mats cling to rocks in tidal zones, photosynthesizing when light permits. Deep sea vents continue to release mineral-rich fluids, hosting specialized organisms. Even when the surface appears lifeless, the oceans maintain pockets of continuity, preserving the potential for recovery. Water, in its abundance and adaptability, ensures that life is never fully extinguished, merely transformed. The planet's slow cycles teach patience. Rivers carve valleys over millennia. Glaciers advance and retreat over tens of thousands of years. Ocean currents shift gradually. Atmospheric chemistry evolves over millions. Life responds to these changes with equal slowness, adapting, migrating, or transforming. Observing these rhythms, we begin to appreciate the temporal scale of Earth's processes. Nothing is immediate. Everything unfolds gradually, a pattern of slow persistence that sustains life across deep time. In reflecting on water, air, rocks, and life together, we notice a quiet harmony. Each system interacts with the others, sustaining equilibrium while permitting change. Currents shape climates, mountains influence rainfall, life transforms chemistry, and chemistry regulates temperature. Disturbances occur, yet the system absorbs them, adjusting subtly over time. Life thrives not despite variability, but because of it, evolving within constraints that simultaneously challenge and nurture. And so, in observing these patterns, we recognize the profound interdependence of Earth systems. Oceans sustain life while regulating climate. Atmosphere shields and moderates. Rocks and tectonics recycle essential elements. Life itself contributes to chemical balance and ecological stability. These systems are neither perfect nor static. They are dynamic, resilient, and intricately interwoven, forming a foundation for the diversity of life that has persisted for billions of years. Even as we reflect quietly in the present, we are witnessing a snapshot of ongoing processes that began long before us. The water cycling through clouds, rivers, and oceans today has existed in similar forms for billions of years. The winds shaping landscapes, the currents moving heat, the microbes adapting to niches. These processes are both ancient and continuous. In noticing them, we reconnect with a planetary rhythm that extends far beyond human experience, a rhythm of endurance, balance, and slow, patient adaptation. The atmosphere surrounds Earth like a protective veil. Invisible yet essential, it mediates temperature, filters radiation, circulates moisture, and carries gases that sustain life. It is both shield and conduit, quietly regulating conditions on the surface. Consider its composition. Nitrogen, the most abundant gas, provides stability. Oxygen, produced over billions of years by photosynthetic organisms, enables the energy transformations necessary for complex life. Carbon dioxide, though a small fraction, traps heat, supporting climates suitable for oceans and forests. Trace gases, such as ozone, absorb harmful ultraviolet radiation, preserving organisms that rely on DNA integrity. This delicate balance has persisted for eons, allowing life to flourish without immediate threat from external extremes. From the earliest moments of life, the atmosphere and oceans have been intertwined. Microbes in ancient seas began releasing oxygen, slowly transforming the chemistry of the water and the air above. This oxygenation did not happen uniformly. It was episodic, gradual, and at times perilous for life forms that evolved in an anaerobic world. The first great surge of oxygen, occurring more than 2 billion years ago, triggered dramatic changes. Many organisms could not survive this chemical shift. Yet this event paved the way for the evolution of complex, multicellular life, illustrating how planetary systems interact to shape possibilities for life. Weather is the immediate expression of atmospheric dynamics. Air masses move across continents, carrying heat, moisture, and energy. Storms form at boundaries where these air masses meet, releasing rainfall that nourishes ecosystems. Winds drive ocean currents, transporting thermal energy from equatorial regions toward the poles. Seasonal cycles, influenced by Earth's tilt, generate predictable patterns that allow species to synchronize reproduction, migration, and growth. Even small variations in atmospheric conditions can ripple through ecosystems, influencing food availability, species distribution, and long-term survival. Clouds, ephemeral as they are, play a pivotal role. They regulate sunlight, reflect heat, and redistribute water across continents. The formation and movement of clouds depend on temperature, topography, and moisture. Rain falls where it is needed, replenishing rivers, lakes, and aquifers. Snow accumulates in mountains, storing water that melts gradually and sustains life downstream. The atmosphere and hydrosphere function together, maintaining a continuity of resources over space and time. Air is not passive. It interacts chemically and physically with the surface of Earth. Volcanic eruptions release carbon dioxide and sulfur compounds, influencing climate and soil chemistry. Forests release volatile organic compounds that can participate in cloud formation. The ocean exchanges gases with the air, maintaining equilibrium in carbon dioxide and oxygen levels. Every interaction, no matter how subtle, contributes to the stability and adaptability of the planet's systems. The atmosphere also acts as a record of planetary history. Ice cores contain bubbles of air trapped thousands of years ago, revealing past concentrations of greenhouse gases. Variations in isotopic ratios inform us about past temperatures and precipitation. These natural archives allow scientists to reconstruct climate changes, volcanic events, and even large-scale shifts in ecosystems. The atmosphere, in combination with oceans, rocks, and life, forms a system that is simultaneously active and reflective, shaping conditions while preserving their memory. Earth's magnetic field interacts with the atmosphere in ways that protect life. Charged particles from the sun would strip gases from the planet without this shield. The field deflects radiation, ensuring that the atmosphere remains intact and functional over billions of years. Solar storms, which could otherwise erode the upper atmosphere, are largely absorbed by this protective barrier. Life benefits quietly, continuously, without conscious awareness of the shielding taking place above. Climate is the result of these interactions, the cumulative effect of atmospheric composition, ocean currents, solar energy, and planetary geometry. Stable climate patterns allow ecosystems to evolve and adapt over long time scales. Ice ages and warm periods occur naturally, and species respond through migration, adaptation, or extinction. The slow pace of these changes allows life to find equilibrium with environmental conditions. Even extreme events, while destructive locally, contribute to long-term resilience and diversity by creating new ecological opportunities. Oxygen, one of the atmosphere's critical components, illustrates the delicate interplay of life and planet. Early photosynthetic microbes gradually increased oxygen concentrations, creating challenges for anaerobic life forms. This shift, often called the Great Oxidation Event, fundamentally changed the chemical and biological dynamics of Earth. Oxygen enabled higher energy metabolic pathways, which allowed for greater organismal complexity. Yet it also created reactive compounds that could damage cells, requiring life to adapt protective mechanisms. Here is an example of balance and challenge of a planet and its biosphere co-evolving in response to chemistry and energy flows. Carbon dioxide similarly plays a central role regulating temperature. Its concentration influences the greenhouse effect, trapping heat and stabilizing climate over geological time. Volcanic activity releases CO, while chemical weathering of rocks removes it gradually. Photosynthesis and respiration cycle it through ecosystems. Small shifts in this balance can trigger global cooling or warming. The resilience of the planet lies in the dynamic interplay between sources and sinks of carbon, moderated by life itself. Forests, soils, and oceans act as buffers, smoothing fluctuations and maintaining habitability. The atmosphere also mediates light and radiation. Ozone in the stratosphere absorbs ultraviolet radiation, protecting DNA and allowing complex life to thrive on land. The scattering of sunlight creates the colors of dawn and dusk, but it also regulates energy distribution across latitudes. The tilt of the planet produces seasonal variations in sunlight intensity, influencing vegetation growth and animal behavior. These cycles, repeated year after year, provide predictability that supports life's rhythms and evolutionary strategies. Life, in turn, influences atmospheric chemistry. Microbes in the soil and oceans produce gases that affect climate and cloud formation. Plants release oxygen and volatile compounds that participate in chemical cycles. Even human activity, though recent in geological terms, has altered carbon dioxide and methane levels, demonstrating how organisms can influence atmospheric balance. Over billions of years, these feedback loops between life and atmosphere have maintained a planet capable of supporting increasingly complex ecosystems. The atmosphere is also the medium for energy transport. Wind distributes heat, moisture, and particles. Hurricanes, monsoons, and trade winds move energy and nutrients across vast distances. Local weather influences migration patterns, reproductive cycles, and feeding behaviors. Global circulation patterns maintain relative stability, preventing extremes from becoming permanent. The subtlety of this energy transfer is remarkable. Storms may appear destructive, yet they are part of a larger system that sustains life over long timescales. Temperature gradients between equator and poles drive ocean currents. Warm water moves poleward, cool water returns toward the tropics. This conveyor belt of energy maintains thermal equilibrium, supports nutrient cycling, and influences atmospheric pressure patterns. Life depends on these predictable flows. Plankton in nutrient-rich waters feeds small fish, which in turn feed larger predators. Marine ecosystems, both near the surface and in the deep ocean, are shaped by these energy and nutrient transfers. Atmospheric pressure itself creates zones of wind circulation, influencing precipitation patterns and deserts. High-pressure regions produce arid climates. Low-pressure regions promote rain and vegetation. Seasonal shifts expand and contract these zones, shaping plant communities and animal populations. Life adapts to these patterns with intricate timing, using cues from day length, temperature, and rainfall to coordinate reproduction, migration, and growth. Even subtle interactions matter. Dust from deserts fertilizes oceans with iron, stimulating plankton blooms. Volcanic ash enriches soils, supporting forests. Clouds reflect sunlight, moderating local and global temperatures. Each of these processes may appear minor in isolation, but together they maintain planetary habitability and ecological diversity. Earth's systems are not static. They are dynamic, integrated, and self-regulating in ways that sustain life across vast scales of space and time. The atmosphere also records extreme events. Layers of ice-trap particles from volcanic eruptions, wind-blown dust, and pollen. These archives provide windows into the past, allowing scientists to reconstruct ancient climates, track evolution, and understand how Earth responds to perturbations. Atmospheric memory is subtle yet profound. It reflects the ongoing dialogue between life, energy, and chemistry, preserving the evidence of interaction for those who learn to read it. Finally, the atmosphere connects Earth to the broader cosmos. Sunlight drives photosynthesis, energy flows, and climate systems. Cosmic rays influence cloud formation and chemical reactions. The planet's rotation shapes wind patterns, while its orbit regulates seasons. These celestial factors, combined with Earth's intrinsic systems, create the conditions in which life can emerge, persist, and adapt. The atmosphere is simultaneously protective, nurturing, and responsive, a dynamic interface between the surface and the universe beyond. As we reflect on the atmosphere, we notice its role in linking water, rock, and life. Rain nourishes plants, winds shape landscapes. Carbon dioxide cycles maintain temperature. Oxygen supports respiration. Microbes and forests feed back into these cycles. Life depends on the atmosphere, and the atmosphere responds to life. The resulting harmony is not static perfection, but dynamic balance, sustained over billions of years through processes both predictable and variable. In contemplating Earth's atmosphere, we are reminded of the patient complexity of planetary systems. Stability is achieved not through rigidity, but through constant adjustment, feedback, and adaptation. Life emerges, persists, and evolves within these boundaries. Energy flows, chemical cycles, and physical processes all interact, creating a planet capable of supporting the astonishing diversity of life we see today. The atmosphere, though invisible to most, is the breath of Earth. It is a living archive, a circulatory system, a shield, and a medium of communication across continents and oceans. It is both ancient and immediate, simultaneously recording the past and sustaining the present. Observing it, we begin to see how Earth's systems operate in concert, how life and planet are entwined, and how subtle balances create conditions that allow existence itself to persist. Beneath oceans and continents lies a surface that is not as fixed as it might seem. The ground we walk upon, the cliffs we climb, and the mountains we admire are part of an outer shell that is in constant motion. Earth's crust is fractured into great plates, massive segments of rock that drift slowly upon the softer mantle below. This movement is so gradual, it is imperceptible on a human timescale. Yet, over millions of years, it reshapes the surface entirely. Continents break apart, drift across the globe, and eventually collide again. Oceans open, widen, and close. What feels stable beneath our feet is, in truth, dynamic and restless. The science of plate tectonics reveals that continents are not permanent fixtures, but temporary configurations. Once, all land was joined in a single supercontinent called Pangaea. Before that, there were others such as Rodinia and Gondwana. Each supercontinent assembled over eons, and then fragmented, setting in motion cycles of separation and collision. These cycles, stretching across hundreds of millions of years, have shaped climate, ecosystems, and the course of evolution. When continents cluster near the equator, they influence ocean currents and climate patterns differently than when they are dispersed toward the poles. The arrangement of land and sea has always guided the possibilities of life. Mountains rise when plates collide. The Himalayas, still growing today, formed when the Indian plate pushed into Asia. The Andes were created as an oceanic plate slipped beneath South America. These mountains do more than decorate landscapes. They also wind patterns, redirect rainfall, and serve as reservoirs of fresh water. Rivers born in snowy peaks carve valleys and floodplains, delivering sediments and nutrients to lowlands. Life thrives in these regions, nourished by the gifts of tectonic uplift. Volcanoes are another expression of Earth's restless crust. When magma from the mantle breaches the surface, it releases gases, minerals, and heat. Volcanic eruptions can devastate local environments, yet they also enrich soils, build islands, and release essential gases into the atmosphere. Some of the most fertile lands on Earth lie on volcanic deposits. Civilizations throughout history have settled near volcanoes, despite the risks, drawn by the fertility of the soil and the abundance it supports. Even destruction is followed by renewal. Forests reclaim lava fields, and coral reefs grow on submerged volcanic slopes. Earthquakes are reminders of this constant movement. Stress builds along faults as plates press, slide, or grind past each other. When the stress is released, the ground shakes, sometimes gently, sometimes catastrophically. Though frightening, earthquakes are part of the same slow engine that recycles crust and drives the evolution of landscapes. They break rock into fragments, create new landforms, and in their aftermath leave soils that water and wind gradually transform. Over time, life adapts to the shifting ground, finding niches even in the scars of seismic activity. Plate tectonics does more than reshape continents and oceans. It plays a vital role in regulating Earth's climate. When volcanic gases rise into the atmosphere, they add carbon dioxide that warms the planet. When mountain ranges form, they expose fresh rock that weathers chemically, pulling carbon dioxide out of the air and cooling the climate. Subduction, the process in which one plate sinks beneath another, carries carbon-rich sediments back into the mantle, completing a cycle that has operated for billions of years. This long-term carbon cycle prevents runaway warming or cooling, maintaining temperatures within a range where liquid water and life can persist. Consider how the movement of continents influences the distribution of life. When land masses separate, populations of plants and animals are divided. Isolation encourages divergence, leading to the evolution of new species. Marsupials in Australia, distinct from placental mammals elsewhere, reflect such isolation. When continents collide, species once separated come into contact again, sometimes competing, sometimes intermingling. These grand migrations and exchanges shape ecosystems as profoundly as climate or geography. Evolution is guided not only by the struggle within species, but also by the slow choreography of drifting continents. The ocean floor provides evidence of this ceaseless motion. Ridges where plates diverge release lava that solidifies into new crust. As the seafloor spreads outward, magnetic minerals align with Earth's magnetic field, recording its polarity at the time of formation. These alternating stripes, symmetrical on either side of ridges, are a geological diary of planetary magnetism and plate movement. Subduction zones, where oceanic plates descend into the mantle, recycle this crust. In these cycles, we see Earth's ability to renew itself, maintaining a balance between creation and destruction. Mountains, volcanoes, and earthquakes may seem destructive, yet they are essential to the richness of the biosphere. The nutrients locked in rocks are gradually released through weathering, carried by rivers, and deposited in soils and oceans. Phosphorus, calcium, and iron, all vital for life, are made available through the grinding, fracturing, and melting of crust. Without tectonic processes, nutrients would eventually be depleted from ecosystems. Life would stagnate. Instead, the constant renewal of land and sea supports the ongoing vitality of the biosphere. The distribution of continents also affects ocean currents, which regulate climate and nutrient cycling. When continents cluster together, circulation patterns change, altering heat transport across the planet. The opening of the Atlantic Ocean redirected currents, influencing rainfall and temperatures across continents. The rise of the Isthmus of Panama altered ocean flow, strengthening the Gulf Stream and affecting global climate. Even subtle changes in geography can cascade into profound ecological consequences. The presence of plate tectonics on Earth is itself remarkable. Among the rocky planets of our solar system, Earth alone shows this global process. Mars has great volcanoes, but no plate movement. Venus has a surface reshaped by volcanism, yet no evidence of drifting plates. The Moon is geologically quiet. On Earth, the combination of internal heat, water in the mantle, and a relatively thin crust allows plates to move. This motion has been essential in maintaining climate stability and recycling elements over geological timescales. It is one of the features that make Earth not only habitable, but persistently habitable across billions of years. Geology and biology are inseparable. The rise of oxygen in the atmosphere was influenced by tectonics, which exposed minerals that reacted chemically with early gases. The diversification of life was influenced by the creation of shallow seas along continental margins, habitats rich in nutrients and sunlight. Mass extinctions were often triggered by volcanic events or changes in ocean circulation tied to tectonic shifts. Evolution and extinction, diversity and adaptation all unfold against the backdrop of moving continents and restless crust. From the perspective of deep time, the planet has never been still. What we see today is one frame in a film that stretches back billions of years. The continents will continue to drift, assembling again into a new supercontinent in the far future. Mountains will rise, erode, and rise again. Oceans will open and close. The ground beneath us is temporary, not permanent. Yet this impermanence provides the conditions for life to continue, adapt, and explore new possibilities. The restless crust is both foundation and catalyst. It provides the platform on which ecosystems grow, and it sets into motion the cycles that regulate climate and nutrients. It creates challenges in the form of earthquakes, eruptions, and shifting landscapes. Yet it also creates opportunities, fostering diversity and resilience. Life is not simply adapted to a static world. It is adapted to change itself, to movement, to the slow but certain rearrangement of land and sea. In contemplating the restless crust, we come closer to understanding how Earth sustains life over deep time. It is not stability that defines this planet, but balance within motion. Continents drift, mountains rise, volcanoes erupt, and earthquakes shake. Each of these processes disrupts and renews, destroys and creates. Together, they form a planet in dynamic equilibrium, a world that has sustained life for billions of years and will continue to do so for as long as its internal fire and external balance remain. Deep beneath the surface, far below mountains, oceans, and even the restless plates of the crust, lies the heart of Earth. It is not solid in the way a mountain is solid, nor fluid in the way an ocean is fluid. Instead, the planet's core is a layered sphere of molten and solid iron, nickel, and other dense elements. It is invisible to us, yet it shapes everything about the surface we know. The core powers the magnetic field. It drives convection currents that move continents. It stores and releases heat that has persisted since the planet's formation more than 4.5 billion years ago. Without this hidden furnace, Earth would not be the same living world. The core is divided into two parts. The outer core is molten, a churning sea of liquid iron and nickel that flows slowly, driven by heat rising from the inner layers. Within it lies the inner core, a solid sphere that remains intact despite temperatures hotter than the surface of the sun. Immense pressure keeps it from melting completely. The interplay between these two layers, solid inner and liquid outer, generates a dynamo effect. This dynamo produces Earth's magnetic field, an invisible shield that extends far into space. The magnetic field is more than a scientific curiosity. It is a protective barrier that preserves the atmosphere and shields life from harmful cosmic radiation. The Sun constantly releases streams of charged particles, known as the solar wind. Without protection, these particles would strip away the gases surrounding Earth, leaving the surface exposed and barren. Mars, with a weak magnetic field and thin atmosphere, bears the scars of such exposure. Venus, lacking a protective shield, is bombarded by solar particles that interact directly with its dense atmosphere. Earth, by contrast, has retained its air and water in parts because of the magnetic cocoon created by the dynamo within. This protective field is not uniform. It bends and shapes itself around the planet, compressed on the side facing the Sun and trailing into a long tail on the far side. Within this field, charged particles spiral and dance, producing the auroras at high latitudes. Curtains of green and red light shimmer in polar skies, visible reminders of the invisible shield. These displays, though beautiful, are also practical indicators of the deep processes within the Earth and the energy of the Sun beyond. The core also drives the slow churning of the mantle above. Heat from radioactive decay and primordial formation escapes outward, setting in motion convection currents. These currents push and pull the tectonic plates, creating mountains, earthquakes, and volcanoes. In this way, the core influences not only the invisible field around the planet, but also the visible surface we inhabit. It is the engine of both protection and transformation. The persistence of liquid metal in the outer core is itself remarkable. Over billions of years, the planet has cooled, but the heat within remains sufficient to maintain fluidity. As the inner core gradually grows, solidifying from the inside out, it releases latent heat that sustains convection. This delicate balance has allowed the dynamo to continue for billions of years. If the outer core were to solidify entirely, the magnetic field would weaken, exposing Earth to conditions similar to Mars. Yet for now, and for the foreseeable future, the hidden heart continues its ceaseless motion. Magnetism influences more than atmospheric retention. Migrating animals such as birds, sea turtles, and even some bacteria are sensitive to the field, using it as a compass for navigation. Long before humans discovered the utility of lodestones and compasses, life itself had evolved to perceive and respond to magnetic cues. This connection between biology and geology, between living organisms and the iron heart of the planet, illustrates the deep integration of systems. The core is not only a geological phenomenon, but a factor in the very patterns of life. The magnetic field is not constant, it shifts and wanders. The poles drift slowly, and over geological time, they even reverse, with north becoming south and south becoming north. These reversals are recorded in rocks on the ocean floor, where iron minerals align with the field at the time of formation. Stripes of alternating polarity is the history of magnetic reversals stretching back millions of years. Life has persisted through these changes, adapting to fluctuating conditions, demonstrating once again the resilience of ecosystems. The inner core itself may not be perfectly uniform. Some studies suggest it has distinct regions, perhaps growing unevenly or crystallizing in patterns shaped by deep processes. Though hidden, it leaves clues in the way seismic waves travel through the planet. Earthquakes send vibrations that pass through layers differently, allowing scientists to infer composition and structure. These vibrations, like distant echoes, reveal the nature of realms we can never visit directly. Our knowledge of the core comes not from sight, but from listening to the trembling of the earth. In contemplating the core, we see the importance of what is unseen. The stability of climates, the persistence of air, the beauty of auroras, and the fertility of volcanic soils all trace back to processes occurring thousands of kilometers beneath our feet. The surface is the expression, but the cause lies within. Earth is not just a sphere of rock with a thin veneer of life. It is a dynamic system, alive with energy from its center outward. Comparisons with other planets highlight the uniqueness of Earth's internal dynamics. Mars, smaller and cooler, lost its magnetic dynamo long ago. Its atmosphere thinned, and its surface became exposed to radiation. Venus, though similar in size to Earth, lacks plate tectonics and has no protective magnetic shield. Its dense atmosphere, dominated by carbon dioxide, leads to extreme greenhouse conditions. Earth alone among the rocky planets maintains a balance of internal heat, fluid motion, and magnetic shielding. This balance has preserved conditions suitable for life over billions of years. The inner core continues to grow slowly, millimeter by millimeter each year, as the planet cools. This growth releases heat that sustains the dynamo. It also releases light elements into the outer core, further stirring convection. Far in the future, the outer core may solidify, and the magnetic field may fade. But for now, the engine runs steadily, unseen yet essential, an enduring guardian of the surface world. When we look at the stars, we rarely think of the core beneath us. Yet it is as vital to our survival as sunlight from above. The core and the sun are in dialogue, one providing energy from afar, the other providing protection from within. Life exists between these two forces, shielded, nurtured, and given time to evolve. The story of Earth cannot be told without the story of its hidden heart. The shield of Earth is not invulnerable. Solar storms occasionally disrupt satellites, power grids, and communications. These disturbances remind us of the energy constantly flowing from the sun and the importance of the planetary defenses we often take for granted. Yet even in these moments, the core continues its work, deflecting and absorbing, preserving an atmosphere that life can breathe. The magnetic field is also a reminder of impermanence and change. The slow drift of the poles, the cycles of reversal, the uneven growth of the inner core all speak to a planet that is never still, never finished. What we see as stability is in fact the product of ongoing motion, balance achieved through constant adjustment. The ground beneath our feet and the air we breathe are sustained by a process unfolding far out of sight. In reflecting on the hidden core, we realize that habitability depends on more than surface conditions. The tilt of the axis, the presence of oceans, and the balance of atmosphere all matter, but so too does the invisible shield generated deep within. Without it, the planet might have lost its air and water long ago. Life would have faced challenges perhaps too great to overcome. The heart of the earth, unseen and unvisited, is a quiet architect of the living world. The restless crust above and the protective field around are connected by the furnace within. Tectonics and magnetism, volcanoes and auroras, earthquakes and animal migrations all trace back to the hidden energy of the core. To contemplate Earth is to understand not only the beauty of mountains, forests, and seas, but also the unseen depths that sustain them. Life is possible not just because of the conditions we observe directly, but because of the hidden processes we cannot see, yet upon which everything depends. The oceans cover more than 2/3 of Earth's surface, vast reservoirs of water that define the planet from space. They appear boundless, stretching beyond horizons, yet they are more than simple expanses of liquid. They are engines of climate, cradles of life, and archives of history. Every wave, every current, and every tide is part of a system that has endured 4 billions of years. To understand Earth, one must understand its oceans. Water is an extraordinary substance. It is liquid over a wide range of temperatures. It expands when it freezes, and it dissolves a vast array of minerals and gases. These properties shape not only the chemistry of oceans, but also the possibilities of life. Ice floats, insulating liquid water below and preventing entire seas from freezing solid. This stability allowed life to persist even during periods of global glaciation. Water's ability to absorb and release heat moderates climate, smoothing extremes of temperature between seasons and across regions. Its solvent capacity enabled the chemical reactions that gave rise to early life and continues to sustain biological processes today. The oceans are layered. Sunlight penetrates only the uppermost zone, where photosynthesis occurs. This illuminated layer supports plankton, algae, and plants that form the base of marine food webs. Below lies a twilight zone, where light fades and strange adaptations allow survival in dim conditions. Deeper still, darkness reigns, and life depends not on sunlight, but on nutrients sinking from above or on energy derived from chemical reactions at hydrothermal vents. Each layer has its own communities, each adapted to pressures, temperatures, and resources specific to its realm. Currents circulate through these layers, driven by wind, temperature, and salinity. The great conveyor belt of thermaline circulation moves warm water from the equator toward the poles and returns cold, dense water to the tropics. This circulation regulates global climate, redistributes nutrients, and connects ecosystems thousands of kilometers apart. A drop of water that begins near the surface in the North Atlantic may sink, travel the depths of the ocean, and resurface centuries later in the Pacific. In this way, the ocean is not only a present environment, but a vast memory, storing heat, carbon, and nutrients across time. The chemistry of seawater reflects interactions between rock, atmosphere, and life. Sodium and chloride, the components of salt, are delivered by rivers eroding land and concentrated by evaporation. Carbon dioxide dissolves in water, forming carbonic acid and influencing pH. Marine organisms extract calcium and carbonate to build shells, which accumulate on the seafloor and eventually form limestone. In this cycle, the ocean acts as both a reservoir and a regulator of carbon, moderating the balance between atmosphere and rock. Life and chemistry are inseparable here. Microbes mediate reactions, phytoplankton draw down carbon during photosynthesis, and ecosystems influence the chemistry of entire seas. The tides, guided by the gravitational pull of the moon and the sun, are daily reminders of cosmic connection. Twice each day, oceans rise and fall, flooding estuaries, stirring sediments, and redistributing nutrients. Tides shape coastal ecosystems, creating habitats that are alternately submerged and exposed. Organisms living in tidal zones are adapted to constant change, clinging to rocks, burrowing into sand, or timing their activities with the rhythm of the water. Human cultures have long measured time by tides, fishing and traveling according to their predictable cycles. They are among the oldest and most reliable patterns on Earth. Storms interact with oceans in complex ways. Hurricanes draw energy from warm waters, growing in intensity as they move across seas. In turn, they mix the upper layers, redistributing heat and nutrients. Though destructive on land, these storms are part of the balance of energy between ocean and atmosphere. Even gentle winds stir the surface, creating waves that carry energy across great distances. The constant movement of water prevents stagnation, sustains oxygenation, and supports ecosystems from coastlines to the deep sea. The ocean floor is as varied as the surface of continents. Vast plains stretch for thousands of kilometers, punctuated by ridges where plates diverge and trenches where plates converge. Hydrothermal vents, where seawater interacts with magma, release minerals and gases that support unique ecosystems. Here, life thrives without sunlight, deriving energy from chemical reactions involving hydrogen sulfide and other compounds. The discovery of these communities revealed that life can exist in conditions once thought impossible, expanding our understanding of what biology can be. The oceans also hold records of climate and history. Layers of sediment accumulate slowly, preserving microfossils, chemical signatures, and isotopic ratios that reveal past temperatures, salinity, and biological activity. Cores extracted from the seafloor show cycles of ice ages and warm periods, volcanic eruptions, and even changes in vegetation on land. The ocean is not only a driver of present conditions, but also a library of past environments, written in minerals and microfossils rather than ink. The soundscape of the ocean is another dimension of its presence. Whales sing across hundreds of kilometers, fish produce clicks and hums, and waves generate constant background noise. Sound travels far in water, serving as communication for countless species. Human activity has added to this soundscape, with ships, sonar, and drilling. For life in the sea, sound is as important as sight or scent on land, a medium of interaction shaped by the properties of water. Life began in the oceans. The first cells floated in salt water, using dissolved minerals to catalyze reactions. For billions of years, the oceans were the sole domain of life, evolving complexity from single-celled organisms to multicellular forms. Even after life colonized land, oceans remained the foundation of global ecosystems, producing oxygen, recycling nutrients, and buffering climates. They are both origin and sustainer, the cradle of life and its enduring home. The diversity within oceans is immense. Coral reefs, though occupying a small fraction of surface area, host more species than most ecosystems on Earth. These reefs build slowly as coral polyps secrete calcium carbonate skeletons that accumulate over centuries. Mangroves and seagrass beds shelter fish and invertebrates, stabilize coastlines, and capture carbon. Open oceans, though appearing empty, teem with plankton that form the basis of food webs. Deep trenches harbor a unique species adapted to crushing pressures and eternal darkness. Every habitat, from sunlit shallows to abyssal plains, supports life shaped by its specific conditions. The resilience of oceans is matched by their vulnerability. Pollution, overfishing, and climate change alter chemistry, disrupt food webs, and stress ecosystems. Rising carbon dioxide increases acidity, affecting organisms that build shells and skeletons. Warming alters currents, storms, and ice cover. These changes remind us that oceans, though vast, are not limitless. They are sensitive systems that depend on balance, just as the atmosphere and crust do. Yet life within them has endured mass extinctions, ice ages, and warming periods before. The oceans adapt, though the forms of life within them may change. Reflecting on the oceans, one sees not only water, but a dynamic system that integrates with every other part of the planet. They exchange gases with the atmosphere, erode and deposit sediments on the crust, cycle nutrients through ecosystems, and archive history in their depths. The ocean is both surface and depth, present and memory, constant and changing. It is the connective tissue of Earth, linking continents, climates, and life into one system. As with the atmosphere and crust, the oceans remind us that stability emerges from motion. Currents flow, tides rise and fall, storms mix layers, and sediments settle. Through this ceaseless activity, conditions suitable for life are maintained. The ocean is never still, yet it is always present, offering continuity across deep time. To contemplate it is to recognize the scale and patience of planetary systems and the intricate ways in which water, chemistry, and life are entwined. The biosphere is the sum of all life on Earth. It is not confined to a single place. It stretches from deep ocean vents to high mountain peaks. It lives in soils, in rivers, in clouds, and in the thin films of water that coat rocks. Wherever conditions allow chemistry to sustain metabolism, life finds a way. It may be sparse or abundant, microscopic or immense, but it persists. To understand Earth, one must see the biosphere as a separate layer added onto geology and atmosphere, but as a woven thread that runs through them. Rocks provide minerals, atmospheres provide gases, oceans provide solvents and heat balance. Life takes these resources and transforms them. It alters chemical cycles, it changes the face of continents. It breathes in one form and breathes out in another. Over billions of years, the biosphere has been both a product of Earth's conditions and an engineer reshaping those same conditions. Microbes were the first architects. They appeared early in a world with little oxygen, using chemical reactions with iron, sulfur, and methane. They consumed gases from volcanic vents and ocean chemistry. They released byproducts that slowly accumulated in air and water. Stromatolites, layered structures made by cyanobacteria, still exist in a few quiet bays today. They are relics of a time when simple organisms ruled the planet and left their mark by building microbial reefs. These organisms changed the world not by intention, but by metabolism. Their waste oxygen altered the chemistry of the atmosphere and oceans. That waste became the foundation for new kinds of life. The biosphere thrives on cycles. Carbon is exchanged between air, water, rock, and organisms. Nitrogen moves from atmosphere to soil and back again, transformed by microbes that can break the strong bonds of nitrogen molecules. Phosphorus comes from rock and flows through food webs until it is locked again in sediments. These cycles are not linear. They are loops that return again and again, moving energy and matter through countless generations. Life depends on them, and life maintains them. Without microbes to fix nitrogen, plants would starve. Without plants to release oxygen, animals would suffocate. Every form of life depends on the invisible labor of others. The biosphere is not evenly distributed. Rainforests teem with species, while deserts appear barren, but hold hidden resilience. Coral reefs dazzle with diversity, while polar oceans sustain food webs with microscopic algae beneath the ice. Grasslands, wetlands, and mangroves each have their rhythms. Some ecosystems pulse with rapid growth and decay. Others move slowly, storing carbon for centuries. Together, they create a mosaic that wraps the planet in green, blue, and every shade of life. The feedback between life and environment is subtle and powerful. Plants draw carbon dioxide from the air, reducing greenhouse warming. At the same time, forests release water vapor, influencing clouds and rainfall. Phytoplankton in oceans not only feed fish but release compounds that affect cloud formation. Termites in savannas digest cellulose and release methane, contributing to atmospheric chemistry. Coral reefs protect coastlines and shape wave patterns. Beavers dam streams, changing landscapes, creating wetlands, and supporting new species. Life is not a passive passenger on Earth. It is an active participant in shaping landscapes, climates, and atmospheres. Mass extinctions show how fragile the biosphere can be and how resilient it can become. When a meteor struck 66 million years ago, ecosystems collapsed. Forests burned, oceans acidified, skies darkened. Yet within a few million years, biodiversity flourished again. Mammals spread, birds diversified, new plants evolved. The biosphere rebuilt itself, not in the same form, but in new patterns. Life persists even when individual species or lineages vanish. The biosphere is both delicate and enduring, vulnerable to disruption, but capable of renewal. Humans are a recent part of this story. We are one species among millions, yet our influence reaches everywhere. We cultivate crops that cover vast areas, altering nitrogen and carbon cycles. We build cities that change local climates and hydrology. We burn fossil fuels, releasing carbon stored for hundreds of millions of years. We transport species across oceans, connecting ecosystems that once evolved in isolation. In doing so, we have become a geological force. Our presence is now part of Earth's record, a layer of plastics, metals, and altered sediments that will endure long after us. Still, the biosphere is not only about large-scale impacts. It is also about countless small interactions. The symbiosis between fungi and plant roots, exchanging nutrients for sugars. The migration of birds spreading seeds across continents. The pollination of flowers by insects guided by scents and colors invisible to us. The decomposition of fallen leaves into soil by beetles, worms, and microbes. Every action echoes through ecosystems, linking organisms into webs of exchange. One of the most striking features of the biosphere is cooperation. Competition exists, but cooperation allows stability. Lichens are fungi and algae living as one organism, surviving where neither could alone. Coral reefs are partnerships between coral animals and photosynthetic symbionts. Human bodies themselves are ecosystems, hosting trillions of microbes that help digest food, protect from pathogens, and shape immune systems. Life often succeeds not by outcompeting, but by joining forces. The biosphere also demonstrates the importance of limits. Ecosystems have carrying capacities. To many grazers and grasslands thin. To many predators and prey collapse. Too much nutrient runoff, and lakes suffocate. These limits are not fixed but shift with climate, geology, and time. The biosphere works within balances, adjusting to conditions. When limits are crossed, ecosystems change. Some recover, others transform permanently. Consider the Amazon rainforest. Its trees recycle water, generating much of their own rainfall. If enough forest is lost, rainfall decreases, and the system risks shifting into a savanna. The resilience of the biosphere depends on thresholds. Push too far, and stability gives way to new states. Earth has crossed such thresholds many times in deep history. Ice ages advanced and retreated. Deserts expanded and shrank. Yet through it all, life endured, finding niches, evolving, diversifying. The biosphere is also a communicator. Pollen travels on vines, insects, and rivers. Seeds float across oceans. Migrating whales carry nutrients between poles and tropics. Salmon bring marine nitrogen into forest soils when they return to spawn and die. These exchanges link distant places, reminding us that ecosystems are not isolated, but connected by invisible threads of migration, wind, and water. Even the air we breathe carries the signature of life. Oxygen exists in high concentrations only because of photosynthesis. Trace gases like methane, nitrous oxide, and dimethyl sulfide are products of metabolism. If a distant observer studied Earth's atmosphere, they would know life exists here. The biosphere makes itself known even to those who cannot see its forests or oceans. The fragility of the biosphere lies in its reliance on balance, but its power lies in adaptability. Life adapts to heat, cold, acidity, pressure, and scarcity. Extremophiles thrive in boiling springs, salt flats, and Antarctic ice. Microbes survive in rocks deep underground. Seeds remain dormant for centuries, then sprout when conditions allow. Life bends, shifts, and transforms. This adaptability is why the biosphere has persisted for billions of years, despite asteroid impacts, volcanic cataclysms, and shifting continents. When seen from above, Earth is not only a blue planet, but a green one, alive with vegetation, alive with movement. Satellites capture forests breathing in carbon dioxide in summer and exhaling in winter. They record algae blooms in oceans, spreading like living paintings. These global rhythms reveal a planet in constant flux, guided by life as much as by physics and chemistry. The biosphere is the heart of Earth's story. It is where geology, water, and air come together in living form. It is not separate from rocks or weather, but a continuation of them, transformed into metabolism and growth. To walk through a forest, to stand by a tide pool, to listen to birdsong at dawn is to hear Earth speaking through its biosphere. It is to be reminded that we are part of the same system, breathing the same air, drinking the same water, and sharing the same cycles that have endured for eons. Beneath our feet, far below the crust and mantle, Earth hides a restless secret. At its center lies a core of iron and nickel, part solid, part liquid, turning slowly but steadily. This movement of molten metal generates something invisible yet indispensable: a magnetic field, vast and protective, stretching far into space. Without it, Earth would be a very different world, perhaps a lifeless one. The magnetic field shields the planet from charged particles streaming from the sun. The solar wind, a constant outflow of protons and electrons, flows across the solar system like a storm of invisible dust. Without protection, this wind would strip away atmospheres, erode oceans, and bombard surfaces with radiation. Mars, smaller and with a weaker core, lost much of its magnetic field early in its history. Over time, solar wind stripped its atmosphere until only a thin veil remained. On Earth, the field deflects most of these particles, guiding them around the planet like water around a stone in a river. Yet some particles do enter, funneled by magnetic lines near the poles. When they collide with atoms in the upper atmosphere, they create shimmering curtains of color. The auroras, dancing lights in polar skies, are the visible expression of Earth's shield. What we see as beauty is in fact protection, energy from the sun dissipated harmlessly in waves of light. The auroras remind us that the invisible shield is active, dynamic, and enduring. The generation of this field comes from the geodynamo. As Earth cools, the outer core of molten iron flows, driven by convection and the rotation of the planet. This movement creates electrical currents, which in turn generate magnetic fields. The process sustains itself, a feedback loop of motion and magnetism. The inner core, solidifying slowly, releases heat and lighter elements, fueling convection and keeping the dynamo alive. For billions of years, this engine has run without pause, unseen yet vital. The magnetic field is not fixed, it shifts and wanders. The magnetic poles drift, sometimes slowly, sometimes rapidly, across hundreds of kilometers. Over geologic time, the field has even reversed completely. North became south, and south became north, dozens of times. These reversals, recorded in the magnetic signatures of rocks on the ocean floor, reveal a restless system. Yet life has persisted through them. The shield never vanishes entirely. It weakens, it flips, but it endures, continuing to protect atmosphere and biosphere alike. Magnetism leaves its mark in stone. As lava cools, magnetic minerals aligned with the field, recording its direction. These magnetic memories are preserved in rocks, providing a map of past field orientations. By studying them, scientists trace the history of reversals and movements. In this way, the invisible becomes visible, written into the very crust of the Earth. The ocean floors, spreading from mid-ocean ridges, show stripes of alternating polarity, evidence of reversals stretching back millions of years. The magnetic field also interacts with cosmic radiation. High-energy particles from beyond the solar system constantly strike the atmosphere. Without the field, more of them would reach the surface, damaging DNA, altering chemistry, and perhaps making life as we know it impossible. Instead, the field deflects many and modulates the flux of others. It is a silent guardian, its strength felt in the very survival of life on land. Yet protection is not perfect. Some cosmic rays do reach the surface, contributing to mutations and changes in living organisms. These rare interactions, though often harmful, also drive diversity. Mutations provide the raw material for evolution. In this sense, the interplay of shield and radiation shapes the story of life, balancing preservation with change. The shield does not eliminate danger, but moderates it, creating space for life to flourish, while still allowing the sparks of novelty. The field also connects Earth to the Sun in another way. Magnetic storms occur when bursts of solar wind, driven by flares or coronal mass ejections, collide with the magnetosphere. These storms can disrupt satellites, power grids, and radio signals. To us, they appear as disturbances, inconveniences, or even hazards. But in the larger context, they are reminders of the ongoing dialogue between Earth and Sun. The field does not isolate the planet. It mediates a relationship, absorbing, deflecting, and channeling energy across space. The presence of a magnetic field is not guaranteed for every planet. Venus, nearly Earth's twin in size, lacks a significant one. Its slow rotation and internal dynamics do not generate the same dynamo. As a result, its atmosphere is exposed more directly to solar wind, though its density offers some protection. Mars, once more Earth-like, cooled too quickly. Its core solidified, and the dynamo shut down. The difference between these planets and Earth is not just mass or distance from the Sun, but the persistence of an active interior. The shield is born from heat within, from the slow cooling of the planet itself. This reveals another truth. Earth's magnetic field is part of a larger system of internal energy. Plate tectonics, volcanism, and the geodynamo all arise from the planet's interior heat. This heat, left over from formation and enriched by radioactive decay, drives cycles on scales of millions of years. It moves continents, builds mountains, fuels eruptions, and sustains the shield. Without it, Earth would be geologically still, atmospherically vulnerable, and biologically diminished. The dynamo is not just an invisible barrier, but a link between deep time and daily survival. Beyond protection, the field offers orientation. Many species sense magnetism and use it for navigation. Birds migrate across continents guided by the invisible lines. Sea turtles return to beaches where they were born, using the field as a map. Even bacteria orient themselves along magnetic lines to find optimal environments. These abilities remind us that magnetism is not only an abstraction for scientists or an invisible shield, but a lived reality for countless organisms. The field is part of the biosphere's fabric, woven into instincts and behaviors across kingdoms of life. The field also offers perspective. To stand under the aurora is to witness not only beauty, but a process that has unfolded for billions of years. The light above is energy from 93 million miles away, shaped by a shield born in the depths of Earth. It is a reminder of connection, from core to cosmos, from molten iron to human eyes. The invisible becomes visible, and in that vision, one can sense the scale of planetary processes that sustain us. The magnetic field may one day fade, billions of years from now, as the core cools and convection slows. When that happens, Earth will lose part of its shield, atmosphere will erode, and conditions will change. Yet by then, the sun itself will be changing, swelling into a red giant, transforming the solar system. The shield, like all things, is temporary, but within its span, it has created the space for life to emerge, endure, and reflect on its own existence. The invisible shield is thus more than a scientific phenomenon. It is part of the deep harmony of Earth. Rocks, oceans, atmosphere, biosphere, and magnetosphere are interwoven, each influencing the others. To imagine Earth without its field is to imagine a barren world, stripped and silent. To contemplate its presence is to feel gratitude for the unseen forces that guard us, guide us, and connect us to the greater cosmos. Earth does not exist in isolation. Its story is inseparable from the system it inhabits. The sun, the moon, the other planets, and even distant comets have all played roles in shaping conditions here. To understand why Earth is habitable, we must consider not only its rocks, waters, air, life, and shield, but also its placement within the larger architecture of the solar system. The sun is the source of almost all energy driving Earth's systems. Its radiation warms the surface, drives weather, powers photosynthesis, and shapes climates. The amount of energy Earth receives depends on distance. Too close, and water would boil. Too far, and it would freeze. Earth orbits within a range often called the habitable zone, where liquid water can exist on the surface. This zone is not a narrow band, but a shifting region, affected by atmosphere, reflectivity, and greenhouse gases. Still, Earth's position is fortuitous, balanced between extremes, allowing stability over billions of years. The stability of Earth's orbit is aided by the presence of other planets. Jupiter, massive and distant, exerts a gravitational influence that helps protect Earth from frequent catastrophic impacts. By deflecting or capturing comets and asteroids, Jupiter reduces the number that reach the inner solar system. Saturn, Uranus, and Neptune also play roles, their gravity shaping the architecture of debris and influencing long-term orbital dynamics. The arrangement of planets is not random, but the result of billions of years of evolution, collisions, and migrations. Earth's survival depends partly on this larger balance. The tilt of Earth's axis adds another layer of habitability. At about 23.5 degrees, the tilt creates seasons. Without tilt, equatorial regions would be perpetually hot, poles perpetually cold, and much of the planet uninhabitable. With tilt, sunlight shifts north and south through the year, distributing energy more evenly and allowing diverse climates. Seasons drive cycles of growth and rest, migration and reproduction. They shape ecosystems and cultural rhythms alike. The tilt is stabilized by the presence of the moon, whose gravity prevents chaotic shifts that could destabilize climates. The moon itself is central to Earth's story. It is unusually large compared to Earth, and its origin traces back to a colossal impact early in the planet's history. A Mars-sized body collided with the young Earth, ejecting debris that coalesced into the moon. This impact not only created a companion, but reshaped Earth's rotation, tilt, and internal structure. The moon's gravitational pull generates tides, rhythms that have influenced life for billions of years. It slows Earth's rotation gradually, lengthening days over eons. It reflects sunlight, illuminating nights and guiding species that evolved under its glow. Its very presence has shaped the course of biology and culture alike. Earth's orbit around the Sun is not a perfect circle but an ellipse. Its shape, tilt, and wobble change over cycles of tens of thousands of years, known as Milankovitch cycles. These variations alter the distribution of sunlight, triggering ice ages and interglacial periods. Glaciers advance and retreat, carving valleys and shaping landscapes. Sea levels rise and fall, exposing land bridges and reshaping ecosystems. Life responds, migrating, evolving, adapting. These cosmic rhythms imprint themselves on Earth's surface and history, reminders that climate is not static, but dances to celestial patterns. Asteroids and comets, though often seen as threats, have also contributed to Earth's habitability. In the early solar system, impacts delivered water, organic molecules, and possibly key ingredients for life. Catastrophic strikes, though destructive, reset ecosystems and open paths for new forms of life. The extinction of the dinosaurs was one such moment, clearing niches that mammals eventually filled. Impacts are reminders of both vulnerability and renewal, showing that cosmic events shape biological history. The solar system also provides perspective through contrast. Venus, similar in size and composition, is cloaked in a dense atmosphere of carbon dioxide, with surface temperatures hot enough to melt lead. Mars, smaller and colder, once had rivers and lakes, but lost much of its atmosphere, leaving a dry, frozen desert. Comparing these neighbors reveals the delicate balance that keeps Earth habitable. The same physics and chemistry apply, yet outcomes diverge dramatically. Earth sits in a narrow window where water flows, air supports breathing, and life thrives. The Sun itself is stable, a main sequence star with relatively steady output. Stars more massive burn quickly and erratically, ending in violent supernovae. Smaller stars flare unpredictably, bombarding planets with radiation. Earth's star provides long-term stability, allowing billions of years for life to evolve. This stability is temporary, of course. In several billion years, the Sun will swell into a red giant, transforming Earth beyond recognition. Yet for now, its constancy is the backdrop for every breath and heartbeat. The cosmic arrangement extends beyond the solar system. Earth moves through the galaxy, orbiting the center every 225 million years. It passes through spiral arms, regions of higher density, where supernovae and molecular clouds are more common. These journeys may influence climate, biodiversity, and even extinction rates. The galaxy is not a static backdrop, but a dynamic environment through which Earth travels, shaped by forces far larger than the solar system itself. The night sky, filled with stars, planets, and galaxies, is a reminder of this context. For most of human history, people looked upward and saw patterns, stories, and guides for navigation. Today, we see them with telescopes and instruments, measuring distances, masses, and spectra. Yet the sense of connection remains. Earth is not the center, but part of a vast system, woven into a cosmic web. Its habitability is not inevitable, but the result of countless conditions aligning, from the tilt of its axis to the presence of a stabilizing moon, from the shielding of a magnetic field to the gravitational influence of distant giants. The cosmic arrangement is not permanent. Orbits shift, impacts occur, stars evolve. Yet within its span, Earth has enjoyed a window of stability long enough for consciousness to arise, long enough for species to wonder why conditions are as they are, long enough for stories, science, and reflection. To contemplate this arrangement is to see not only chance, but also the intricate interplay of forces, each shaping the possibility of life on this particular world. Earth is more than geology, more than water, more than air and life. It is part of a cosmic architecture that has allowed stability and change in equal measure. The arrangement is fragile and resilient, precise and dynamic. To reflect on it is to feel both humility and gratitude. Against the vastness of the universe, this planet is a rare place where oceans sparkle, forests breathe, and minds ask questions. The story of Earth is not one of isolated parts, but of interwoven systems. Rocks and oceans, air and life, shields and cosmic patterns all intersect. Each supports the others, each influences the rest. Together, they create a balance that has endured 4 billions of years, a balance fragile enough to shift with a small change, resilient enough to persist through cataclysms. When we step back, we see not random fragments, but a tapestry. Tectonic plates shift, building mountains that alter weather and rivers. Those rivers carry minerals to seas where organisms build shells, which in turn become limestone, storing carbon, regulating climate. Forests breathe oxygen into the sky, while volcanic eruptions release gases that shape temperature. Even extinctions, devastating in their moment, open space for new life, new forms, new possibilities. This balance is not static, it is dynamic, always moving, always adjusting. Seasons turn, ice ages come and go, continents drift. Species evolve, flourish, and fade. The planet has been frozen and overheated, barren and lush, quiet and loud with life. Through all of it, conditions have remained within a narrow band that allows water to flow and life to persist. That is the miracle of Earth, not perfection, but resilience. Resilience does not mean indestructibility. Earth has wiped slates clean many times. It has buried oceans beneath deserts, raised mountains from seabeds, and erased whole lineages. The conditions we experience today are temporary, the product of countless feedbacks and coincidences. They will change again, as they always have. What feels stable is in truth a moment in motion, a pause within cycles that stretch beyond comprehension. And yet, Within this shifting framework, life has not only survived but flourished. From single-celled microbes in ancient seas to forests stretching across continents, from coral reefs glowing beneath waves to flocks of birds crossing hemispheres, life has taken root in every niche. It has transformed air, soil, and oceans, leaving chemical signatures that mark its presence. Most remarkably, life has become aware of itself. From this single planet, beings have arisen who look outward and inward, who ask how it all fits together. That awareness changes the story. Earth is not only a physical system, but also a subject of reflection. We can measure carbon in rocks and oxygen in air. We can trace isotopes, analyze fossils, and map magnetic fields. We can watch tectonic plates inch across the globe and chart the slow precession of the axis. We can model climates past and future. In doing so, we see patterns invisible to the senses, patterns that reveal how fragile the balance truly is. We know, for example, that small changes in greenhouse gases alter climate dramatically. We know that ecosystems depend on delicate interactions between soil, water, and organisms. We know that the shield protecting us from radiation is not eternal, but slowly weakening and shifting. We know that impacts, though rare, can change everything in an instant. To live on Earth is to live within limits set by forces we cannot fully control. And yet, the knowledge itself is remarkable. For most of history, life simply adapted without reflection. Now, life has become aware of planetary systems, able to anticipate, predict, and even influence them. That knowledge is a form of responsibility. To understand balance is to see where it might be disturbed, where resilience could be tested, where fragility might break. Consider water. It is abundant but finite, circulating through clouds, rivers, and aquifers. It shapes civilizations, feeds agriculture, and sustains ecosystems. Yet it can vanish from landscapes when climates shift. It can become scarce through overuse or contamination. To understand water's role is to see how easily balance tips, how quickly abundance can become absence. Consider forests. They regulate air, store carbon, shelter species, and stabilize soils. They arise from complex interactions of climate, geology, and life itself. Yet they are also vulnerable, dependent on rainfall, resistant but not immune to fire, disease, or human activity. To reflect on forests is to see not only beauty, but the fine edge between resilience and loss. Consider the cosmic arrangement. Orbits are stable now, but not unchangeable. Impacts are rare but inevitable in long timescales. The sun is steady, but only temporarily. To reflect on Earth's placement is to see how fragile a habitable window really is, how easily conditions could differ, how unique this moment is within billions of possible configurations. Through all these reflections, one theme returns: Earth is not guaranteed. Its habitability is the result of countless coincidences, interactions, and feedbacks, each reinforcing and balancing the others. Remove one piece, and the whole could collapse. Alter chemistry too far, tilt climate too much, or weaken shields beyond repair, and the system could shift into a state where life as we know it cannot persist. And yet, for now, here it is. Oceans sparkle, forests breathe, air carries the songs of birds and the murmur of winds. Continents drift, mountains rise, and rivers carve valleys. The moon pulls tides, the sun warms days, and the stars wheel overhead. Within all this movement, there is a moment of stability long enough for questions to be asked, stories told, knowledge shared. Perhaps that is the most remarkable feature of Earth, not only that it sustains life, but that it sustains reflection, that it allows a species to notice patterns, to see connections, to imagine causes and consequences, that it allows not only survival but wonder. If Earth were designed, we might imagine it as a vast system where every part supports another. If Earth were accidental, we might see the same result, a balance born of physics, chemistry, and time. Either way, the outcome is the same: a planet where rocks, water, air, life, shields, and cosmic patterns align to create a home. A place where fragility and resilience coexist. A world rare in the universe, perhaps unique, where silence has given rise to voices asking why. So when we look at Earth, we are not only seeing geology or biology, we are seeing a story billions of years long, a story still unfolding. We are seeing the improbable balance that allows us to wonder at all. And if you've journeyed with me through these reflections, I'm grateful. If you'd like to keep exploring questions like this, I invite you to stay connected. A simple way is to follow, subscribe, or share this with others who might also find wonder in the quiet workings of our planet. No pressure, just an open invitation, like a trail left in sand, pointing toward more questions waiting to be asked.